In this video, we're going to be discussing how information systems are acquired or created. We'll be exploring where the software that your company uses comes from. Let's say, for example, that your company now wants to create their own app to allow customers, for example, to place orders. Perhaps Forest City Ducks, a company that creates custom 3D printed rubber ducks, now wants to make an app that allows customers to scan their face and put it on a 3D model of a duck that they can now purchase through the app. How would Forest City Ducks acquire this software? Seems unlikely that there'd be an off-the-shelf solution for this. Would they make it in-house? That would require hiring app developers and would be outside their specialty. Could they outsource the development of the app overseas or even locally? Perhaps, but there are risks involved in that as well. Let's get into it and see how businesses acquire new information systems like this. But first, there's some required readings. Before viewing this lecture, you should read Chapter 10, Acquiring Information Systems Through Projects, in your textbook. There's also some recommended homework problems on MyLab MIS that you should attempt before reading the chapter and watching the video. There are a great way to study for the final exam as well, so I do highly recommend them. With that out of the way, let's now move on to how information systems are acquired. Software applications can be acquired in one of 5 basic ways. The first of which is to buy it and use it as is. This is also called off-the-shelf software, as back in the day you used to have to go into the physical store and purchase it literally off the shelf. These would be boxes that contain the floppy disks with the CD software on it. For example, this is the game Half-Life that I purchased a long time ago, literally off the shelf, I think at a Future Shop. And this would contain, for example, CDs, DVDs, disks of some kind that actually contain the software on it, that you'd then install in the computer. Nowadays, if you want to purchase a game like that, you'd probably connect to a service like Steam and download it over the internet. But if you go into a Best Buy today, you can still sometimes see small shelves with software on it in stores like Best Buy. But they tend to now contain only a little piece of paper with a download code, rather than disks. Regardless of how you purchase the software, this method has the advantage of being relatively cheap and risk-free, but only if there is already existing software that meets your needs exactly, which is rarely the case. For example, it's unlikely that there's some software that Forest City Ducks could buy off the shelf that would be able to scan faces right onto ducks. That's such a specific use case, no one probably sells that software specifically. The next method is to buy it and customize it. Again, this is a type of off-the-shelf software, but with the added ability to customize it. This can be done in one of 2 ways. The first and most common of which is that you would purchase the software with an added contract that states the company you're purchasing it from will customize it for you based on your provided requirements and specification. The second way would be acquiring open source software that comes with the source code that you may edit and make changes to yourself as needed. However, making changes to software is not trivial, and your company would need to hire programmers to make these changes. To carry on with our Forest City Ducks example, there may not be any off-the-shelf software that can scan faces onto ducks. Perhaps there is software for scanning faces in general, for 3D modeling, that could be customized for this purpose. Forest City Ducks might have to make a contract with a company that provides such software to customize it for their needs before delivering it. While this provides a solution that meets their needs exactly, it tends to come at a higher cost in terms of both money and time. Another option is to rent or lease the software. This is normally done for a set period of time on a subscription model where you pay the software vendor on a recurring basis for the duration that you're going to be using the software for. With the advent of cloud computing, we tend to see this a lot in the form of cloud or web-based applications, such as Office 365 or Adobe's Creative Cloud. These are ones that you usually purchase on a subscription basis, and you can access over your web browser in some cases. Leasing or renting has the advantage of potentially being cheaper if you are only using the software for a limited period of time. Things like software upgrades, maintenance, and even in some cases backups of files are provided with the service. The downside is a loss of control, limited customization, and potentially being unable to access your software or the files if the internet's down. Next is to simply build it yourself. This is rather straightforward in concept, but extremely difficult in practice. To create software, you need to hire developers, programmers, system analysts, database administrators, and potentially more roles depending on the size of the software system you are developing. If software development is outside of your business's area of expertise, this can also be extremely risky, as developing software is complex and it's not uncommon for large software development projects to fail. especially when undergone by inexperienced organizations. You can also end up with developers on your payroll with nothing to do if you don't have a constant supply of work for them. The upside is that if successful, you have full control and ownership over the software, and in theory, it could help you gain competitive advantage as no one else has access to the software. The last method is outsourcing. This is where you hire an outside company to develop your software for you based on your requirements. The difference between outsourcing and simply buying and customizing it is that when you outsource the work, you normally retain ownership of it, whereas buying it and customizing it would imply that the software vendor still retains at least some rights to the software. For example, you might not be able to resell or modify the software you buy from a vendor, whereas software that was acquired through outsourcing is normally yours to do with as you please, including reselling, modifying it, and so on. When software development is outsourced to other countries overseas, we call this offshoring. The benefit of outsourcing and offshoring is that it tends to be cheaper than developing the software in-house, especially if you have no existing development team. The downsides are that you have to trust a third party to create the software for you. Normally, the monetary risks of this are actually kind of low, as you only pay a small amount up front. But there could be significant costs in terms of time lost if the project never is completed or it doesn't live up to your expectations. Having the software developed by a third party can also cause issues if you want to modify the software later. That vendor may no longer be around or may charge a significant amount, knowing that you have few other options now. Furthermore, it may be hard to go after an overseas vendor if they should break your contract or agreement and run away with the money, or maybe even sell your software to another party, as you'd have to enforce your contract in another country's legal system. Now that we've covered how software is acquired, I do have one question for you that I'd like you to think about for a few seconds. Based on what we've covered so far in this lecture and the course, do you think that acquiring new software is the same as acquiring a new information system? Are they the same, or are they different, and why? Think back to what an information system is and what software is, and try to come up with an answer. I'll give you a few seconds, but pause the video if you think you need more time. And we're back. And the answer is no, they're not the same. Recall what an information system is, and that it's comprised of 5 components: hardware, software, data, procedures, and people. Software is just one of these components, and most of the time, if you are just acquiring software, you're not acquiring any of these other components. And this is a big problem. Not considering the costs of the extra hardware infrastructure, updating the business procedures, converting data, and retraining your employees is a common mistake that smaller companies make and can be devastating for that company. You need to have plans for how you're going to acquire the hardware, how you're going to set it up and install the software, how you're going to convert any existing data in your database to work with the new software, and how you're going to update all your procedures and retrain your employees. This is no small task, and unless you are purchasing something like enterprise resource planning software or ERP software, that tends to come with things like predefined procedures, you'll need to account for how this new software will fit into your business and its existing information systems. So how do we acquire information systems then? Well, they're normally acquired through projects. Projects consist of a temporary endeavor undertaken to create a unique product, service, or result. In particular, IT projects are projects that have a large information technology component. Now, saying create a unique product here can be a bit misleading. Projects may still involve the purchasing, leasing, or outsourcing of software or hardware components. What's being created here, rather, is the information system as a whole, and tying all those components together, regardless of if they were developed in-house as part of the project or purchased as part of the project's plan. Some examples of IT projects might be installing a new email application, or installing a new CRM system, it's customer relationship management system, or even an enterprise resource planning system that might span the whole company. So all of these systems would also have to be tied into all of the information system components. Remember, that's hardware, software, procedures, people, and data. When thinking about starting an IT project, there are some major considerations before any work can begin. The first of these is the scope or the objective you're trying to achieve. What is the end goal of this project, and how will you know when it's done successfully? It is important to have a realistic scope, as if you keep adding things and saying that the project is going to do and solve everything, you'll likely end up with a project that's way over budget and never finished. The next consideration is the start and end date of the project. Now that may seem simple enough. You just pick some dates on the calendar when you want to start, and when you think it's going to be finished based on how many developers you have and how fast they work. Fortunately, in real life, estimating time to acquire an IT project is extremely difficult, even for large companies that specialize in software development and IT projects. Part of the reason for this is something called Brooks' Law. You may think that your project is running behind, so all you need to do is throw some more developers or programmers at it. Might increase costs, but things should get done on time. Well, not really. In the real world, this rarely works out, and may even make your project later. There's a few reasons for this, including adding people to a project requires setup time for each person to get up to speed and become productive. The other issue is that adding more people requires more communication and meetings, which means more overhead and time spent on communication rather than working. And lastly, not all tasks are easily broken into parts that can be worked on by multiple people. Now you may be thinking, well, maybe the end date's hard, but at least the start date's easy, right? However, that might not be the case either. A lot of things have to be put in place for a big project to start, such as hiring, resource allocation, and committees or board meetings about the project. Another major consideration is the temporary use of resources. What's meant by this is that if you are going to allocate resources and people to work on this project, they can't work on other things that might be more important to your business to function properly. Are you going to hire new developers or programmers for this project? What happens to them after the project's over? There could be a lot of lost opportunities if all of your resources are allocated to this project, such as different projects that might be ultimately more profitable or meaningful to your company. All of this has to be considered before investing heavily in an IT project. And lastly, is it unique? Will this project be something that's unique to either your organization or the industry? If it's not unique, there might be pre-existing off-the-shelf solutions or alternatives to the project. If it's not unique to the industry, there may be pre-existing best practices to follow that could save a lot of planning time. Also, if the project's not unique, you may wish to consider what value and competitive advantage it brings. Does this project help accomplish our business goals and objectives? As you've likely already gathered from me going over these points, it's very hard to estimate some things like time, budget, and scope of IT projects. All of these things have to be considered not only at the start of the project, but constantly evaluated during the project's lifecycle. So how does this tie into IT operations? But first of all, what even are IT operations? IT operations, also sometimes called IT services, are the activities performed by the IT department to deliver services, maintenance, protection, and management of IT infrastructure. This can include things like setting up computer security policies, maintaining production systems and networks, managing databases, and even more mundane things like keeping employees' desktop computers running. We could say that IT operations are concerned with keeping the lights on. That is, keeping everything up and running as it should be. Put it in the most simple terms, these are the guys you call up with your computer problems, and they ask you if you've tried turning it on and off again.
Hello, IT? Have you tried turning it off and on again?
IT projects, on the other hand, are generally aimed at renewing or adapting the existing IT infrastructure. That is, improving, replacing, or creating new systems. Normally, this would be handled by a separate group in the IT department, or in some organizations, a completely different department. This group tends to have a broader and more specialized skill set than those working in regular IT operations. For example, you might need programmers and system analysts rather than computer or network technicians. However, it's important to note that both teams very much still rely on each other for success. Eventually, projects end, and management and maintenance of these systems that are created must eventually shift over to the regular IT department. Similarly, the existing IT infrastructure eventually needs to be renewed or replaced, which results in a new IT project. So there very much is a cyclical relationship between the two teams. Here's figure 10.2 from our text. I think it does a nice job of showing the cyclical nature between IT operations and IT projects. IT projects improve or create new information systems, which are eventually maintained by IT operations. Information systems maintained by operations eventually need to be renewed or replaced, and this becomes an IT project, which once finished becomes a system for operations to maintain, and it goes around and around like this. So while they're very different teams, they are both very much needed for a fully functional IT department that's capable of creating and maintaining projects. I mentioned before that IT projects are very risky. But why is that? Well, to start, all business projects face risk, even ones that are not related to IT. Even if you're not risking money, time invested in a project that's ultimately not successful is time lost that you could have spent on something more productive for your business. There is some debate about just how risky IT projects are compared to any other type of business project, and we find some conflicting numbers in the literature. The Chaos report by the Standish Group states that only 16% of IT projects are completed on time, on budget, and in scope. That's a scaringly low number. Worse still, they also state that 30% are cancelled before any value is derived from them. Fortunately, later research has shown a little bit higher success rate for IT projects, being closer to about 2/3 or 66% of projects being successful. But even then, 25% of them underperform and did not meet some expectations. Even these improved numbers are still abysmally low. But what makes IT projects so risky like this? Well, there are a lot of things that can and will go wrong, and these risks start even before the project begins. Recall that I previously stated that it's incredibly hard to estimate costs and time for IT projects. This leads many projects to be cancelled when they're not delivered on time or if they start going over budget. It's also hard for management to monitor the progress of IT projects, especially if they're not familiar with the technology. They might see what they interpret as no progress on the project and be tempted to cancel it, or they might be fooled into thinking the project is going fine when it's currently a disaster. This is why it's so important for you to have an understanding of the topics we're covering in this course, even if you never plan on being a programmer or a developer. You need to know the technology involved, at least at a high level, so you can properly manage programmers in these types of projects. The next issue is poor planning and documentation. Far too many businesses, and even computer science students working on their assignments, see a problem and try to dive right into coding a solution rather than taking a step back to plan it out. Planning and documenting these projects is critical for their success, and that's why we have a whole field devoted to it called software engineering. It's very hard to coordinate work on a project without an overall picture of what everyone's working on, and how it fits together. Planning and documentation, such as diagrams and models, help us do that. Lack of experience is a big risk too. As I mentioned, you need a specialized team working on IT projects that can be expensive and hard to find. Support's also needed from management that understands the nature of IT projects. Without proper support and resources, IT projects are likely to be cancelled at the first sign of trouble. For IT projects to be successful, they need to have support from the bottom to the top of an organizational hierarchy. Management needs to understand the importance of the project and how it supports the business's goals and objectives. Lack of participation from system users is another big one. After all, who do you think is going to be using the system every day after it's completed? If the end users of the system refuse to use it, or it makes their job harder, all of the time and money invested in the project will have been for nothing. This is why it's so important to include end users of the system in every step of the process, to ensure what you're creating is actually going to meet their needs. Unclear requirements are another big issue. If your developers have no idea what they're creating, it's not going to end well. Even if the project is eventually completed, uncertain or unclear requirements could mean that what you've created does not actually accomplish what you set out to create. To bring back the Forest City duck example, if the app could scan faces and put them on ducks, but not place orders, it'd be useless. Being able to place orders is a requirement that must be stated clearly and in no uncertain terms during the planning phase of the project. The last major risk is the organization simply not having the ability to handle the technical complexity of the project. If you're not familiar with what's possible with the technology you're using, you might create requirements that are not technically possible for your organization to achieve. For example, saying that you're going to create a fleet of self-driving trucks to make your supply chain more efficient might be a great idea on paper, but it'd be unrealistic for most organizations. And a big problem with this is that when outsourcing, there are companies out there that will gladly take your money, saying that they can do anything that you dream up. But then it turns out they ran away with your money. This is why it's so important to know what is currently technically possible and what's unrealistic. Now let's move on to discussing the Systems Development Lifecycle, or SDLC for short. So what's SDLC? Well, it's a process for acquiring information systems that was largely developed through trial and error by early companies experimenting with IT projects in the 1960s. Many early projects met with disaster And based on these failures, developers determined what went wrong and developed standardized processes for creating and maintaining information systems. SDLC breaks the development lifecycle into tasks that are required to successfully create and maintain an information system. These basic tasks are grouped into phases of the system's development that form the development lifecycle. Here we have figure 10.3 from your textbook, which displays the different phases of the SDLC lifecycle and how they're linked together. One important thing to note is that the number of phases in the SDLC varies by organization and author. To keep it simple, our text uses a 5-phase model. Regardless of the number of phases it's split into, the basic life cycle is the same, and starts with the business deciding that they need an information system to accomplish their business goals or objectives. Once the business establishes the need for a new system, the first phase, system definition, can begin. In this phase, management, a committee, or a designated group of employees defines the scope of the new system and assesses its feasibility. Essentially, they are planning what the end goal of the system is, what it should do, and who's going to make it. A critical component of this phase is ensuring that the new system will be in alignment with the organization's competitive strategy and business processes, and that in the end, it will actually improve decision-making. After all, that is one of the main goals of information systems. An additional task in this phase is the feasibility assessment. This is where an organization ensures that the proposed system is feasible in terms of cost and time, as well as that it's technically possible for the organization to create. The result of all these tasks is a formal project plan. The next phase is requirements analysis. In this phase, a project team is created, and they take the project plan and scope document created by management in the system definition phase and attempt to break it down into individual parts called requirements. This involves identifying all the features and functions that the system will perform to meet the goals and scope of the project plan. For example, if we go back to that case of Forest City Ducks and their 3D scanning app, some requirements might be that the user can log in, that they can scan their face, that the face can be put on a 3D duck model, that the user's face can be rescanned if they're not happy with that scan, that the user can purchase the duck using the app, that the duck model is displayed to the user, and that the user can manipulate the 3D model by zooming in, out, rotating it, and so on. The idea here is that we have a detailed list of requirements that can be used both during development to ensure the new system can complete all these tasks, as well as to evaluate if the system has accomplished its goals at the end of the process. Next is the component design phase, which is based on the approved requirements developed in the last phase. In the component design phase, specifications are developed for the hardware and software that will be used in the system. This software could either be developed in-house, outsourced, or it could be off-the-shelf software that's purchased and meets the organization's requirements. This is also where models and diagrams of each component are created. For example, if the system will use a database, the data model is converted into a database design and documented using diagrams such as ERDs or entity relationship diagrams. Procedures for the new system are also created in this stage, including backup and failure recovery procedures. Finally, job descriptions are created for any new employees needed to use and operate this new system. In the implementation phase, the system is finally built. Each component of the software is programmed independently and put together if that software is being made in-house or outsourced. If off-the-shelf software is being used, this would be the phase where it's purchased and possibly modified for the organization's needs. Documentation is also produced in this phase, so the process of maintaining and using the software is simplified later on. Another big task in this stage is testing. Each individual component or unit of software must be tested, as well as the software as a whole after it's integrated together. This testing is normally done by creating and following a test plan. A test plan is a sequence of actions that the tester takes when evaluating the system. The plan includes both normal user actions, as well as incorrect or unusual actions a user could potentially perform. The idea is that you want to cover all possible user actions in your plan, which is why this is a very labor-intensive process. Due to the amount of work involved, testing is usually performed by quality assurance professionals, whose only job is to test the software. This allows your programmers to spend most of their time writing code, and employees who specialize in testing to focus on that part of their job. Skipping or skimping on the testing phase is a recipe for disaster. Imagine if there's a bug in your new system that deletes important records from your database accidentally. Not discovering this until your system is launched could be disastrous, and will cost you more time and money than simply testing the software properly to begin with. Once everything's ready to go, the software is launched. But it's not quite that simple. How are you going to move your users over to the new system? This task of moving users to the new system and converting business functions is called system conversion, and is part of the implementation phase. And there are a few strategies we can take to convert our users to the new system. The first is a pilot program. In this strategy, the organization implements the entire new system, but only gives access to a limited number of users or groups. The advantage of this method is that if something goes horribly wrong, it only impacts a limited number of users, who usually know that they're part of this program, and they expect potential issues. Real-life example of this would be London Hydro's Green Energy pilot program, that gave participants a smart home gateway like this one, that could monitor their power use, and a smart plug, like this one right here, that could be used to turn a specific device on and off. It could also be used to monitor the electricity used by that device. The goal of the project was to eventually offer users more choice in how they were billed for energy use, enable users to monitor their power use of specific devices, and even eventually allow London Hydro to turn off power-hungry devices off remotely during peak power usage times. And it was a good thing that this was a pilot program too, as it did go sort of horribly wrong. Turns out this smart plug here had a few issues, the most significant being that it had a bad habit of catching on fire randomly. Because London Hydro used a pilot program, rather than shipping these out to everyone at once, disaster was averted, and the smart plugs were recalled. Well, most of them anyway. I never gave mine back. The next strategy is phased. In this method, the new system is installed in phases, one component at a time. After a phase is complete, time is given for users to encounter issues, and the results to be evaluated. This continues until the whole system is implemented. The advantage again is the risk is reduced by limiting the amount of systems that are changed at once, and users are allowed to slowly become accustomed to them. The downside is that it's not possible for tightly integrated systems that cannot be easily broken into parts or phases. Real-life example is Western's multi-factor authentication system, or MFA for short, called Duo. Deployment began by only requiring MFA for certain systems, like email, and then it spread to things like MyVLab and their HR system, until all sensitive systems were eventually using MFA. Another common strategy is parallel. In this method, both the completed new system and the old system are run together at the same time, while the new system is being tested. This is probably the most expensive and time-consuming option, as now you have to maintain two systems and ensure the data is duplicated between them. The advantage is that there is very easy fallback if things go wrong. Users can simply switch back to the old system. Real-life example of this is the social media website Reddit, currently running both a new version of their GUI and an old version that you can access at old.reddit.com. And this also highlights another danger. Reddit has been running this old Reddit system now for about 5 years, because there's a large contingent of users that refuse to move over. Now Reddit is stuck supporting both options. The last strategy is plunge, and this is not really a strategy, and is simply just suddenly releasing the new system at the same time you close down the old one. This is cheap, but there's no backup position, and if things go wrong, you have a disaster on your hands. Real-world example of this would be another social media site called Dig. Dig used to be a link aggregator, like Reddit, and one day, just like Reddit, they decided to change their user interface. However, unlike Reddit, they did not run the sites in parallel or phase it in. They simply took the plunge and switched it over. It was a massive failure and hated by most users, and it played a large role in Dig going under after most users migrated to Reddit. Okay, so now we've tested our system and launched it successfully. Now you may be thinking, yay, we're finally done. But remember what we discussed before about the cyclical nature of IT projects. Eventually the new system will need maintenance, and problems like bugs are found. Or there's a change in the business that requires a change to the system. And this is where system maintenance phase comes in. In this phase, any defects in the system are documented, as well as requests for enhancements to the system, like new features. Small defects may be corrected with software packages, updates, or new releases. These fixes are normally prioritized based on the severity of the issue, so it's also important to document the impact it has on the system. And this is where the cycle comes in. Once issues are identified or new features are requested, the life cycle starts again with the system definition phase, which defines the scope for the new features and fixes. This cycle continues over and over again for the life of the system until it's been eventually decommissioned or totally replaced. To give an example, let's say our face scanning duck app was completed and a great success. But there's still a few issues. Perhaps if the user rescans their face too many times in the same session, the app crashes due to a memory leak. Or that we now want to also start 3D scanning faces onto garden gnomes. We would have to start the process over with a new system definition, then requirements analysis, component design, and implementation, until we had a new tested version of the application, and the cycle starts again with new issues and features. Now there is a bit of a problem with the SDLC model, and that is that it follows what we call the waterfall model. And it's called that because each phase flows into the next without any way of going back to the previous stage unless the whole process is restarted. And this is a big problem, as the waterfall model is largely considered to be an anti-pattern. That's basically a fancy way of saying it's a bad idea. The reason why is there's no way to adapt to changes in the business or project environment during development. Perhaps we get to the component design phase and realize we've forgotten an important requirement or feature in our requirements document. Well, there's no way to go back now, and the original team who made the requirements document may not even be around anymore. Even worse, if we make it to the implementation stage and we don't find out about an issue until testing. Perhaps one of the requirements just didn't make sense in practice, or something in the original project scope is just not technically feasible. We would have to go back to the drawing board and at least redesign some of the components and scrap a lot of work. Another common issue is that the needs of businesses are always changing. Perhaps when we started developing our app, iPhones were all the rage. But during development of the project, the market shifts and now the vast majority of people are using Android. This could be a big problem as we've already have our requirements and components designed for iOS. There are a few potential solutions to this. Newer methodologies such as Agile methods and the Scrum approach use 2-week development sprints that are designed to develop smaller components of the system, test them, and then reevaluate to see if any changes to the requirements are required. Teams using this methodology are set up for and expect changes during development, so they're better able to handle changing environments and requirements. This makes the cycle we discussed much shorter, and the project will go through many such cycles before it's implemented or ever finished. Now up to this point, we've been describing the new system as if we'd be developing the software in-house ourselves. But even in this SDLC process, using commercial off-the-shelf software, or COTS software for short, is still a possibility. But as we've discussed, off-the-shelf software might not fully meet the needs of our organization. So how do we determine if COTS is appropriate? And what do we do if it doesn't meet our needs? Well, first we need to take a look at the needs of our organization and the capabilities of the off-the-shelf software, and compare them. During this comparison, we identify any discrepancies between our needs and the software's capabilities. And it would be very rare for there to be no discrepancies at all, as every organization has unique goals and needs. For example, perhaps we want a new system for managing online orders for Forest City ducks. But the COTS software we're looking at doesn't support the customization options we need for each product, as it's not designed for 3D printing. This would be an example of a discrepancy we would need to handle. Next, we would need to decide what we're going to do about the discrepancies, and we have 3 basic options. If possible, we could modify the software to match our needs. Problem with this approach is that it costs money and time, and is only possible if the software is open source, or the software vendor is willing to make the modifications for us. The next option would be to modify the processes, procedures, and data in our organization to match the software, rather than the other way around. Perhaps we wanted the ordering software for Forest City ducks to have options for each product based on the type of the filament used, but modifying the software was not possible. We could change our procedures and processes and data to make a unique product record in our database for every combination of duck and filament type. Not an ideal solution at all, but it might be the most cost-effective versus making our own software. The last option is to simply just live with the problems, if they're not that significant. Perhaps we can just do that step manually. In real life, organizations don't have to just pick one alternative. They can use hybrid solutions such as modifying some parts of the software, but also changing the organization's data to match the format used by the new software. The last topic I'd like to touch on more is outsourcing. Recall that in terms of software development, outsourcing is the process of contracting out software and information system development to a third party. However, outsourcing is not exclusive to software development. Most jobs and business functions can be outsourced to third parties with differing levels of success. Technology has even made it so jobs that we'd traditionally not think of outsourceable are at risk as well. Recall the case of Freshie attempting to outsource their cashiers overseas using video conferencing and tablets that we discussed in one of our earlier lectures. Still remains to see if this will be successful in the long run for Freshie. When jobs are outsourced overseas like this, we call it offshoring, as I mentioned earlier in the lecture. But outsourcing can also be done domestically. Another type of outsourcing that we have not yet discussed, at least not in terms of outsourcing, are application service providers. This is a special form of outsourcing where software applications are rented from a provider on a fee-for-service basis. For example, a company may pay monthly based on the number of users they have, or the amount of resources they're using, such as the size of the data stored on the provider's cloud. Vendors maintain the system on their own website, and clients can access the application through the site. These are essentially cloud applications, and can help reduce costs in the short term, as the service fees are drastically lower than developing your own software. Yet again, an example of this would be Office 365 or Adobe's Creative Cloud. So besides application service providers, why do companies outsource rather than developing their own application? Well, it's an easy way to utilize the experience of a third party that you may not have yourself. If your company is focused on something like 3D printing, you might not have any employees that are qualified to create software, and hiring new employees may not be possible or beneficial if you do not need them after the project is completed. There can also be a significant cost reduction, especially if you are offshoring, as you can exploit lower wages in foreign countries. There's also reduced risks in terms of development, as you normally only pay a small amount upfront, so if the project fails, as IT projects frequently do, you won't be out a significant amount of money. Also, unlike buying or leasing software from other software vendors, you normally retain full ownership of the software you've created through outsourcing. This means that you're free to resell it or modify it in any way you wish without any restrictions. However, outsourcing is not without its risks, the biggest one being loss of control. You're putting all your faith in a third party, possibly from a country you have little ability to enforce contracts in legally, to create your information system. A dishonest developer could potentially steal your intellectual property, or even resell your whole information system to other businesses and eliminate any competitive advantage you'd gain from that new system. You would also be at their mercy if you need any bug fixes or new features added, and they could easily jack up the price or simply disappear, leaving you with an information system you can't maintain. Worse still, if you don't have a dedicated development and testing team, it may be hard to ensure you got what you paid for. How will you know if all of the requirements are met and proper testing has been done? You may also not have gotten any documentation with the new system and have no idea how it works under the hood, making switching to a different vendor extremely expensive, as they'd have to reverse engineer the whole system to learn how it works to fix even the simplest of bugs. All of these potential risks and advantages must be carefully weighed before choosing an option or a vendor. Picking a domestic vendor can help reduce risk, as they'll be more accountable, but this also means an increased cost. And that concludes our discussion on acquiring information systems in Chapter 10 of your textbook. Thank you for watching, and have a great day.